Jethro. I was born in Cali, Colombia, and I studied a degree in chemistry at McGill University in Canada. And then I transitioned into geochemistry, where I studied my PhD under the supervision of Professor A.E. Williams-Jones. And today I'm going to present to you my work of PhD, which is about the potential role of petroleum as an ore fluid in sediment-hosted mineral deposits. So there are many sediment-hosted mineral deposits around the world that show signs of having interacted with petroleum. The images that you can see to the left of your screen are images from the Yankee deposit in Alligator Ridge, which is a Carlin-type deposit in Nevada, USA. As you can see, the ore zone of this deposit contains oily material, like these oil-filled cavities or vugs, and there is a high gold ore grade in these deposits in Nevada. They contain as much as 6 grams per ton gold, which means they're economically mineable. It is very common to find petroleum or liquid hydrocarbon inclusions in the ore zone in this deposit. So as you can see, there is an oil inclusion inside of a carbonate cement. There are many other mineral deposits, not just gold deposits, but nickel deposits, molybdenum, platinum group elements, copper, mercury, uranium. All of these elements exist in sediment-hosted deposits where there appears to have been an injection of petroleum into the system. So the hypothesis that I've been testing for my PhD is whether the petroleum can transport metals from deeper parts of the basin into the ore zone. Now, traditionally, it is believed for sediment-hosted deposits that the predominant ore fluid is hydrothermal fluid or hot brines, but we are investigating the notion that perhaps petroleum is acting as the ore fluid. So in order to test this hypothesis, we devised an experimental method to find out the steady state concentration of different metals in petroleum. In order to do this, we would get a piece of metal wire. In this case, in the picture, it's a palladium wire to test the concentration of palladium in crude oil. And we would dissolve the wire in crude oil inside of a sealed quartz tube. And then we'd place this quartz reactor or this quartz tube inside the oven at different temperatures and leave it to react. After the reaction, we would open the tube, remove the metal wire. Then the oil was ashed inside of a furnace at 550 degrees Celsius for 24 hours. After the ashing, there's a small char that remains at the bottom of the tube. So this ash or this char, we digest with a cocktail of different acids and hydrogen peroxide to make all the metals soluble. And then we dilute and we analyze this solution using ICP-MS or ionized coupled plasma mass spectroscopy. And from this, we can tell the concentrations of the metal in the petroleum. The metal wire was rinsed in toluene. It was vacuum dried, and then the surface of the wire was analyzed using an X-ray technique called X-ray photoelectron spectroscopy. And this technique is used to tell us something about the kinds of chemical compounds that remain attached to the metal wire after reaction with petroleum. So we're trying to see what kinds of compounds have an affinity for certain metals. Here is an example of how we determine the steady state concentration. Basically, we test the concentration of the metal at 5 days, 10 days, 15 days, 30 days, and so on, until we see that the concentration of the metal in the oil plateaus. And whatever this concentration is, we deem it to be the steady state concentration. So we repeated these experiments with 3 different metals, nickel, zinc, and palladium. We did it at 3 different temperatures, 150, 200, and 250 degrees Celsius. We chose these temperatures based on oil window temperatures and oil stability considerations. And we did it for a suite of oils, for 3 different oils. We also calibrated this method by using oil standards of known concentration. And we found that our experiment matched the concentrations of nickel and vanadium in the oil standards. So we know that this methodology has a high level of precision. We also chose 3 different oils. These oils were provided to us by the oil company Statoil, which is now being rebranded as Equinor. The oils have different compositional parameters. They vary quite a bit in terms of these compositions. For the purposes of this presentation, the most important compositional parameters have been highlighted, and these are the thiol content. So thiols are a class of reduced sulfur compounds. Then the other parameter that is important for this discussion is the TAN, or total acid number, which is a measure of the acidity of the oil. And finally, the iron content of the oil we found to also be important. So we were comparing the metal concentration of different metals dissolved in oil to the compositional parameters. So first off, the experiments. Here are the zinc experiments, and here are our results. What we find is that the concentration of zinc in crude oil increases with the acidity of the oil, which means the more acidic the oil, the higher the concentration of zinc that you can dissolve inside of it. Also, zinc concentrations in crude oil increase with temperature. So as temperatures go higher from 150 to 250 degrees Celsius, you are also capable of dissolving more zinc. In our most metal-rich oil, we were capable of dissolving as much as 1,700 parts per million zinc, which is considerably higher than the amount of zinc that has been reported to be soluble in brines or in hydrothermal fluid at this temperature. We therefore consider that zinc is highly soluble in crude oil from an economic perspective. The total acid number, or the acidity of the oil, is strongly correlated to the carboxylic acid content of the oil. So on the right of the screen, you have an image of what carboxylic acids look like. When we analyzed the surface of the zinc wire that had been reacted with the oil, we found that the zinc wire has an affinity for oxygen compounds in crude oil. When you scan the surface of the wire, you see that there are predominantly 4 chemical elements that are attached to the wire. Zinc, because it's a zinc wire, oxygen, carbon, and sulfur. Now, the XPS has a capability which allows you to etch or to remove layers of the wire sequentially using an argon ion beam. And what we found is that as we etch the wire and we remove the surficial compounds that are weakly bound to the surface of the wire, we expose the peaks that have a greater affinity for zinc. So in this case, carbon and sulfur peaks were seen to diminish as we etched the wire, whereas the zinc and the oxygen peaks grew. We therefore conclude that zinc has a high chemical affinity for oxygen in crude oil. Since the carboxylic acid content of crude oil is correlated to the oxygen content of oil, this gives us independent evidence for the complexation of zinc by carboxylic acids in oil. So we have seen that zinc is highly soluble in acidic oils due to complexation with carboxylic acids. And therefore, crude oil is potentially a very good ore fluid for zinc. But we were curious to know whether we can precipitate metals from crude oil to form a mineral deposit. Now, the image to the left is a quick schematic that I've drawn relating to the chemical environment that you find inside of Mississippi Valley type deposits. Mississippi Valley type deposits are a common class of sediment hosted deposit, and it's very common in the ore zone of these deposits, which is these deposits are generally calcite and gypsum hosted. Inside of this calcite or calcitic ore zone, we find large amounts of brine, of crude oil, and of different gases such as CO2, H2S, and methane. The hydrogen sulfide gas in these deposits is of particular interest because hydrogen sulfide concentrations help zinc precipitate from the ore fluid. The hydrogen sulfide is generated through a reaction known in nature as thermochemical sulfate reduction, which is thought to have onset temperatures between 100 and 140 degrees Celsius. This reaction is a reaction between the sulfate or sulfate-rich brines and crude oil. And what happens is that the crude oil becomes oxidized by the sulfate-rich brine, and you form calcium carbonate, you form water, and you form hydrogen sulfide gas. Oil companies hate this reaction because it destroys their oil, but for people who are interested in mineral deposits, this is a very important reaction. So I devised an experiment to imitate the kinds of geochemical conditions found in the ore zone of Mississippi Valley type deposits. I did this by mixing a crude oil that was rich in zinc with sodium chloride brine that was calcium carbonate buffered. And we purged the system with hydrogen sulfide gas to ensure a hydrogen sulfide atmosphere inside of the reaction vessel. This is a close-up picture of the reaction vessel. After 5 minutes of leaving the oil and the brine mixture exposed to hydrogen sulfide gas, we saw little white crystals start to precipitate out of the interface between the oil and the brine. We tested the composition of these crystals using X-ray diffraction, and we found that the crystals were indeed sphalerite, which is the most common zinc ore found in nature and is also the zinc ore that you find in Mississippi Valley type deposits. Here are some examples of bituminous ore samples from the Pine Point, Mississippi Valley type deposit in Canada. The most important thing perhaps to notice of these images is that the samples are highly bituminous, and that this bituminous matter is often derived from petroleum fluids that infiltrated the rocks. So the conventional wisdom for these deposits says that ore metals are transported into the ore zone in basinal brines. These brines will mix with sulfate-rich fluids from the back reef, and the sulfate is thermally reduced to hydrogen sulfide through reaction with the hydrocarbons. However, our hypothesis is that the petroleum, not the brine, might be responsible for transporting the metals into the ore zone in the first place. We also did experiments on palladium, which is one of the noble metals. The experiments show slightly different results. For palladium, we can see that palladium concentrations increase as the thiol content of the oil increases. So the higher the thiol content of the oil, the more palladium that we are capable of dissolving in the oil. Our most palladium-rich oil was capable of dissolving as much as 128 parts per billion palladium, which again is considerably higher than the amount of palladium that you can dissolve in hydrothermal fluids under geologically realistic conditions, like 0.01 molar concentration of sulfur in hydrothermal fluid. The interesting thing with palladium is that as you increase the temperature, it actually becomes less soluble in crude oil. So palladium concentration is highest at 150 degrees Celsius, and then it decreases as you go from 150 to 200, and so on. When we analyze the surface of the palladium wire that has been left to react with crude oil, the thing that is immediately apparent is that the wire is encrusted almost completely by sulfur. And when we analyze the sulfur peak, we see that this sulfur is predominantly in the reduced form, in the thiol form. And while some of these thiols are unbound, a lot of the thiols are actually chemically bonded or chemically attached to the surface of the wire. Also, we can see that the palladium wire in this reaction has been oxidized from palladium 0 to palladium 2. So at the same time that that the thiols in the crude oil are being bound to the palladium is being oxidized. Here we give the example of the bituminous Kupferschiefer deposit, which contains as much as 1,900 parts per million palladium in the Lubin mine in Poland. As you can see, the ore-containing layer, the Kupferschiefer itself, is actually quite thin, ranging from maybe 30 to 40 centimeters thick up to several meters thick at most in some locations. The interesting thing about this layer is that it contains abundant polycyclic aromatic sulfur hydrocarbons, or PASHs, which is a class of compounds commonly found in petroleum. This has led some authors to believe that the Kupferschiefer may have actually been infiltrated by carboniferous crude oils coming from deeper parts of the basin. The ore-forming temperatures in the Kupferschiefer, which are between 80 and 140 degrees Celsius, are similar to the oil window temperatures, which extend from 80 to 160 degrees Celsius. Finally, I'm going to present my nickel results. With nickel at 150 degrees Celsius, for the 3 oils that we tested, we see very low solubilities of nickel in crude oil. However, as we increase the temperature to 200 and then 250 degrees Celsius, we see that one of our oils, in this case oil C, which is our most thiol-rich oil and our most iron-rich oil, it suddenly takes off in terms of concentration, much more than its counterparts. When we analyze the surface of the nickel wire, we also realize that nickel has a high affinity for sulfur in crude oil. So before etching, the nickel wire is coated with nickel, oxygen, carbon, and sulfur. But after etching the wire, only sulfur remains. If we have a closer look, for example, the first picture on the top left of the screen is it's the surface of the wire after reaction with our most thiol-rich oil. And what we can see is that the surface of the wire, the sulfur peak, entirely is composed of reduced sulfur compounds, meaning that thiols or reduced sulfur compounds have a high affinity for nickel. We also reacted these metal wires, the nickel wires, with crude oil at room temperature. And as you can see, the sulfur spectrum of the oil that remained bound to the wire at room temperature has both oxidized and reduced sulfur peaks. So what this seems to be indicating is that not only does nickel have an affinity for sulfur in crude oil, but nickel may also be helping to catalyze the reduction of sulfur from its oxidized state into its reduced state. We also did the same sort of experiments with oil B. Oil B is, as you can see from the picture at the bottom right of the screen, at room temperature, oil B is composed predominantly of oxidized sulfur compounds, but after reaction with nickel wires at 200 degrees Celsius, this oxidized sulfur has been reduced to thiols or to reduced sulfur. So this means that even for oils that don't have a high thiol content, nickel actually can help catalyze the reduction of these metals. This is X-ray photoelectron spectrum of the iron that remains attached to the wire. So what we find is that as we react crude oil with the nickel wire, iron from the oil starts to become incorporated into the surface of the wire. So at the same time that sulfur is being reduced, we are also seeing that iron is participating in this reaction as well. So the redox reactions that are involved in catalyzing the reduction of sulfur using nickel, iron also probably participates in these redox reactions. In terms of the geological sites that we're interested in, one of my colleagues called Kyle Henderson recently visited one of the field sites, which is in Yukon, Canada. And in this field site, we see that the ore horizon, which is usually no more between 10 and 30 centimeters thick in these hyper-enriched black shales, it's a highly bituminous ore horizon with a lot of pyrobitumen, and it contains up to 7.9 weight% nickel. Also, an interesting point is that within 10 meters, so 10 meters below the ore horizon, we have found these extremely large pyrobitumen veins, which are also highly enriched in nickel. And we consider that these pyrobitumen veins may be the relics of hydrocarbon fluids that became emplaced in the rocks and froze up over time. So, in conclusion, zinc, nickel, and palladium are all highly soluble in crude oil from an ore deposit perspective. The solubility of zinc and nickel increases with temperature, but the solubility of palladium decreases. Zinc is preferably dissolved by petroleum that is very acidic, that is to say, petroleum that is very enriched in carboxylic acids. During a reaction known as thermochemical sulfate reduction, we produce large amounts of hydrogen sulfide gas, and this hydrogen sulfide gas stimulates the precipitation of zinc from crude oil. Now, nickel and palladium have a high affinity for thiols in petroleum. The thiol content of petroleum is actually known to increase a lot during thermochemical sulfate reduction. And so we consider that petroleum that has undergone thermochemical sulfate reduction will be better at dissolving metals like nickel and palladium. We also consider that metals like nickel and palladium may not only be more soluble in crude oils with high concentration of thiols, but they might actually promote thermochemical sulfate reduction by serving as catalysts for the reaction. And this basically concludes my presentation and the research findings for my PhD. Thanks a lot for listening. And if you have any questions, I'm happy to answer.
I got a question.
Yes.
What is the end of ashing the sample at the beginning?
Okay. So basically, we have to find a way of getting the metals into solution. So after the ashing, you are left with a very small amount of carbonaceous material at the bottom of your glass tube. And then this carbonaceous material, we react with a little bit of hydrogen peroxide and nitric acid and hydrochloric acid. And you start to see that the carbonaceous material starts to bubble and starts to oxidize. And then eventually all of the metals become dissolved into solution. And then we can dilute this solution and then analyze it using ICP-MS.
Okay.
Hola, Jethro. Tengo una
Hola.
pregunta, pues la voy a hacer en español, pues. Sí. Jethro, bueno, la pregunta es si, por ejemplo, en estos momentos hay algún yacimiento que esté en explotación, pues algún yacimiento de esta tipología. Si esto, pues obviamente lo veo que está muy relacionado con los depósitos de tipo Mississippi Valley, pero si hay, digamos, como alguna propuesta de volver esto como una tipología como tal de yacimientos minerales, ¿qué perspectivas hay sobre esto? Gracias.
Como en términos de exploración.
Sí, como tipología de yacimiento mineral, no sé, así como por decir algo, como los Mississippi Valley, como los sulfuros masivos volcanogénicos y tal.
Okay.
Digamos, Eso.
Sí, entonces, normalmente son depósitos minerales que se encuentran en rocas sedimentarias. Entonces, los Mississippi Valley son solo una clase de depósitos que son hospedados en este tipo de rocas. Pero en realidad, cualquier depósito que, por ejemplo, cualquier cuenca sedimentaria que tenga, por ejemplo, rocas como, no sé cómo se diga, shale, que son como que buenas rocas para producir petróleo y que parecen haber sido expuestas al tipo de temperaturas que son necesarias para producir petróleo, y que también demuestren existencia de petróleo dentro de la zona mineralizada. Son buenos candidatos para el tipo de procesos que mencioné en mi charla. En realidad hay muchas clases de depósitos que se pueden formar o que posiblemente se pueden formar de esta manera. Se sabe, por ejemplo, que ocurre en depósitos de oro, de cobre, de por ejemplo, elementos nobles como platino y paladio. Todos estos tipos de elementos se encuentran concentrados en rocas sedimentarias y en muchos casos, no solo en la clase de Mississippi Valley Type, eh, existen, por ejemplo, inclusiones de fluidos dentro de los mismos minerales que se explotan. Entonces, por ejemplo, estaba mostrando los depósitos por ejemplo, los depósitos Carlin Type que se encuentran en Nevada y también se encuentran mucho en el sur de China. Estos depósitos tienen altos contenidos de oro, pero también tienen inclusiones de petróleo adentro de ellas. En general, el modelo que más se utiliza para este tipo de depósitos es que la gente piensa en general que se forman a partir como del metabolismo de las bacterias en la interfase entre los sedimentos cuando se están formando y el océano. Entonces, piensan que ciertos tipos de bacteria, como las bacterias que reducen el azufre, son importantes para formar este tipo de depósitos. Existen algunos problemas con estos modelos, por ejemplo, metales como el níquel son muy poco solubles dentro de aguas hidrotermales y también existen en muy bajas concentraciones en el océano. Entonces, por ejemplo, si vemos una roca sedimentaria que tiene o que muestra inclusiones de petróleo y que tiene alto contenido de níquel, por ejemplo, entonces de pronto es más factible que se haya formado con procesos que involucren el petróleo que con procesos hidrotermales. No sé si eso ayuda a contestar esa pregunta.
Sí, sí, Jethro. Muchas gracias.
¿Alguien tiene alguna otra pregunta para Jethro?
Yo tengo una pregunta.
Sí,
La voy a hacer en inglés, ¿listo?
perfecto.
In the last deposit that you show in Yukon is in Canada, the host rock in which the mineralization was in place, it was sedimentary rocks, or which kind of rock were there? Yeah.
Yes. So all of these deposits. So it doesn't matter the element. Zinc, nickel, copper, palladium. They are all hosted in sedimentary rocks. Sometimes they are carbonate sequences, but most often, like the ones in the Yukon, they are hosted inside of shales or black shales, which are the same kinds of rocks that you usually find petroleum being produced in. The interesting thing with the Yukon ones is that the mineralization is hosted in rocks that are very bituminous, and they extend for a very, very large area. They outcrop in the Yukon, they outcrop discontinuously for maybe about 800 kilometers. But in China, there is a deposit known as the Zunyi deposit, which is actually 2,000 kilometers long, and all of the ore, or all of the nickel and molybdenum and platinum group elements are found within a 10 centimeter thick ore horizon. So it's extremely thin, the ore horizon, and these rocks outcrop for 2,000 kilometers from one side of China all the way to the other. And the China ones are particularly curious because there is a lot of evidence of what they call microbitumen, so little particles of bitumen that seem to indicate that the ore zone of the deposit was brecciated by a petroleum fluid. Now, the other really interesting thing about the ones in southern China, which are a direct analog of the ones in the Yukon, is that they are roughly 542 million years old, which is the same age as the Cambrian explosion, which is it's the largest explosion of life on our planet. So we consider that maybe whatever the ore forming processes that were involved in forming these deposits may also be important processes for the formation of life on our planet. So maybe mineral deposits, petroleum systems, and the major life events on the planet are all interrelated.
Okay. Okay, perfect. Thank you.
Thank you.
Sorry, got another question.
Yes.
So you said that in order for increasing the nickel concentration, the TSR, the thermochemical sulfur reaction, has to pass, no?
Uh-huh.
So what will I see on for example, on a fluid inclusion within a mineral? Will I see petroleum? Means the petroleum is going to be messed up, or?
So I know in some deposits, like the Mississippi Valley type deposits of the Canning Basin in Australia, they have inclusions within the sphalerite. You have sometimes you have fluid inclusions, like normal fluid inclusions with brine, but actually most of the inclusions in the major deposits of the Canning Basin are petroleum inclusions that look very similar to the one that I had like in my introductory slide. So there are these sort of like brownish, yellowish inclusions. The oil in them, they know that the oil is being transported from a different part of the basin, from deeper in the basin, because they've done biomarker studies. and they can tell that the organic matter in these inclusions is more mature and from a different source than the rest of the organic matter, like surrounding the deposit. If it's undergone thermochemical sulfate reduction, what usually happens is you destroy your source of oil. So you get much smaller amounts of oil, but the oil is much more rich in thiols. I don't think a thiol-rich oil looks particularly different to regular oil, but it usually will contain much higher concentrations of metals. The common thing to find in these deposits is like if it has undergone thermochemical sulfate reduction, is you will see that there is a lot of hydrogen sulfide gas in the deposit, and yeah, this commonly occurs in petroleum. This reaction occurs a lot in petroleum systems, maybe between 3 and 7 kilometers deep below the surface, but which is around the same sort of depth that you find Mississippi Valley type deposits as well.
Okay, so let me check if I understood. So the thermochemical sulfur reaction, it doesn't mess up the oil, it just has to happen in order to have thiols, an amount of thiols.
It does kind of mess up the oil. So if you have a large amount of oil and it reacts, it becomes oxidized by the sulfate. So let's say in most oil systems, you have some amount of water and some amount of petroleum. Usually, because the petroleum is less dense than the water, it floats on top of the water. But you usually have both petroleum and water in petroleum systems. Now, if you reach temperatures of like 100 degrees Celsius or more, what starts to happen is the sulfate in the water reacts with the petroleum and you oxidize the petroleum. So you actually get less and less petroleum. And the petroleum becomes of a worse and worse quality, for example, to use in your automobile. Because it gets full of thiols, and this is an impurity that is very difficult to remove. But so this is probably very bad news for petroleum companies, but it is probably very good news for people who are interested in mineral deposits, because it might mean that as you destroy your petroleum, you form smaller and smaller amounts of petroleum that are more and more enriched in thiols.
I got it, thank you.
Okay, thank you.
¿Alguien más tiene alguna otra pregunta? Bueno, parece que no.
I have a question pretty quickly.
Yes.
Hi, thank you very much for your talk. Very interesting. I was just wondering if you had any constraints of the amount, just like the order of magnitude of both oil and brines that you would need in order for creating like mineralizations that are economic, let's say.
Yeah, so off the top of my head, I do not remember the numbers, but I know, for example, that if you take the reserves of, for example, if you take the reserves of the shale that is known as the Gold Wire Shale in Australia, the Gold Wire Shale occurs in sedimentary rocks just below the lead zinc deposits. It's actually a class of Mississippi Valley type deposits. It's the Kajiput deposit and the Polaris deposit in Australia. If you take the reserves of the Gold Wire Shale and you say that these oil has a concentration of about 1,000 parts per million zinc, which we actually believe that you could transport a lot more zinc than this in crude oil, especially if the oil is very acidic. Because the oils in our experiments are actually, in natural terms, they are not that acidic. Like some oils reach total acid numbers of like about 16 milligrams potassium hydroxide per gram of oil. The ones in our experiments only have acidities of 2.9 milligrams of KOH per gram of oil. So if you take 1,000 ppm oil with zinc, and you take it into account using the reserves of the Goldwire Shale of the Canning Basin, it's more than enough oil to form the entirety of the zinc in the Kajiput deposit. And we have another example that we've cited in our papers, which is if you take there's another petroleum system called the Carboniferous Rotliegend system, which is in the North Sea of Europe, which directly underlies the Kupferschiefer deposit stratigraphically. Again, the reserves of this petroleum system, which are right on the edge of the Kupferschiefer deposit, would be more than enough to form all of the palladium reserves at the Kupferschiefer if you were transporting just 100 parts per billion palladium, which again, we consider that could be much higher concentrations of palladium in oil, particularly if the oil's undergone TSR. The exact numbers I don't remember off the top of my head, but I do have them in my publications.
Okay, thank you very much.
Thank you.
Bueno, parece que ahora sí tienen la última oportunidad de preguntar a alguien si alguien quiere preguntar. Bueno, parece que no es más. Querido, muchas gracias. Que te vaya muy bien en el postdoc. Qué rico que te hayas vinculado a esta iniciativa. Muchas gracias a los chicos de los capítulos y a Mateo por haber vinculado esta charla tan chévere. Nada, quedamos en contacto. Chao, chao.
Perfecto, muchísimas gracias y ojalá podamos seguir en contacto y sí, a futuro.
Muy bien, feliz día para todos y nos vemos ahorita a las 11 en nuestra próxima charla de cuarentena con Geociencias para hablar de la bioestratigrafía. Chao, chao.
Hasta luego.